Okay, so today let's try to solve this problem called minimum operations to achieve at least k peaks. So basically in this problem we are given nums and k, so then we need to return the minimum of operations such that there will be k peaks in nums. So what does that mean? So first of all, peak just means that the number has to be greater than the left one and also strictly greater than the right one. So you might ask, what happens if this I is the last one? Wouldn't I plus 1 be overbounding? That's right. So if it is the last one, we won't use I plus 1. We will just use 0. The same goes for I minus 1. If this is the first one, we don't I minus 1 because again, this will give us our bound. That's why we just use the n minus 1, which is the very last one, if I happens to be 0. So one operation just means that you can pick any numbers in any index and increase that by 1. Okay, so let's take a look at the first example. We are given 2, 1, 2, and k we are given 1. So the answer, we should be returning 1. Why? Because, well, first of all, we need to take one peak out of these nums. So right off the bat, there is no peak at all. So 2 is not a peak because this is not strictly greater than the left one because this is the same value. 1 is also not a peak because this is actually strictly smaller than left and right. And this 2 is also because it's not strictly greater than the right one, which happens to be wrapping around to be looking at the first one. So, but because we can just increase nums2, which is the third one, by 1, and then it will make this peak. So imagine this will be like 3 and this will be peak because this is strictly greater than the left one and then also strictly greater than the first one. The same goes for the first one. We can also increase the first one by 1 and then this will also be peak. But we are only asking the cost here, so it doesn't matter that much which one we choose. We just need to return the cost. So we used one operation to make the k, which is 1, peak appear. So that's why returning 1 here. So let's take a look at the second example. We are given 4, 5, 3, 6 and k equals 2 and we should return 0. Why? Because, well, as you can see, 5 and 6 are already peak because it is strictly greater than the left and then also strictly greater than the right. The same goes for 5, right? It's strictly greater than 4 and then also strictly greater than 3. So let's take a look at the third example. First example, we're given 3, 7, 3 and then k we are given 2 and we should return -1. It's because no matter which one we increase, well, first of all, we are looking to find 2 peaks in a nums length equals 3, which is kind of impossible if you think about it. Because the best we can do is choosing every other element to be peak, if that makes sense. So for example, this 7 and this 3, they cannot be both peak because the definition of peak is that you have to be strictly greater than the left one and strictly greater than the right one. So that means adjacent element can never be both peak because if they are both peak, this kind of violate the definition of a peak, if that makes sense. So that's why we're just return -1 here. So lastly, let's just take a look at the constraint before we move on to the solution. So we can see n can up to 5,000 and then nums I will be 10 to the power of 5 from -10 to the power of 5 to positive 10 to the power of 5, and then k can be as large as n. So just right off the bat, we kind of know that the solution might somewhere lie between n squared or n times k because of the constraint like that. Again, if this is like a n log n solution, this n will be much larger, like 10 to the power of 5 or something. So yeah, that's like the initial view of the problem. Let's think about how can we solve it. Okay, so to solve this problem, we can think about it recursively. So let's decide a DFS I k is first peak. So what does that mean? Well, this formula basically means the minimum number of operation needed to solve from I all the way to the end, where we still have to find k more peak element, and the first element has been picked or not as the Boolean value in the is first peak. So initially it will be DFS 0, k, and then forced. That will be our final answer, but how do we do the induction step? So let's assume for each I, if you think about it, for each I we basically have two options, right? We either pick this element to be a peak or we don't pick this element as a peak. So in this formula, if we pick this element as the peak and then we have to do DFS I plus 2 and k minus 1. So why I plus 2 is because if you think about it, I plus 1 and I cannot be both peak. So if we choose this element, meaning nums I, to be one of the peak, then I plus 1 need to be a non-peak because if they cannot be both peak at the same time, that will violate the very definition of the problem. So that's why the best we can do is I plus 2 and k minus 1 because obviously we chose this element as the peak, then we have one less peak element to choose for, and then the third parameter is the is first peak Boolean value, we will set this to true if we are going to pick this element as one of the peak, and this I index happens to be the first one. Otherwise, we will just inherit this first peak from the parent. And then this max left-hand side, right-hand side minus current value is just the way to calculate the cost to make the current element as a peak. This will give us the solution or the minimum answer if we pick this element as one of the peak. But what happens if we don't pick this element as one of the peak? That's even easier. We just do DFS I plus 1 and then we don't touch k and we don't touch its first peak. So the end case is that if we reach 0, then we have nothing to choose for and we can just return 0. Or I reaches the end. That means that we don't have any elements that we can pick to be a peak. In that case, if we are not reaching 0, we're just gonna return something like an infinity. Or this one is a little bit more tricky. I reaches the end is not the end of the element, but the very last element, and is first peak. That's actually the same principle that we have to do I plus 2, is because first element is actually adjacent to the last element. So if we have chosen the first element as the peak, and it basically means that the last element cannot be a peak. So if we have chosen the first as the peak and it reaches the end, the last one of the array, and we just terminate that. At the starting point, as we mentioned, we're going to start from DFS 0, k, 4. So this is I, this is k, and this is its first peak. Yeah, that's pretty much all the intuition. Let's think about how can we implement the solution. Okay, so as usual, we are going for the brute force solution first. Let us go for a DFS definition. So what we want to do here, again, we have explained it before, but I'm gonna explain it one more time. We're gonna have this DFS I, k, and its first peak. Basically, we want to find the minimum of operation to solve from I all the way to the end when there are k remaining peaks to choose from, and also if the first one has been chosen as peak or not. And initially, we're just going to initialize n as the num size, and then we're going to use the infinite like a constant later, and then we're going to define our DFS recursive call. Then we're going to start doing the recursion. So first, we're going to handle some base case. If remain is 0, it means that we have nothing to choose anymore. We don't have any more peaks that we have to choose, which just return 0. Otherwise, if I greater or equal to n, it means that we don't have any nums to pick from. And also, if we reaches the last element and the first element happens to be a peak, that also means that we cannot do anything to the last element. So it is effectively the same as reaching the end as well. So what happens if we reach the end, but we also still have some remain? It means that we cannot solve in this case, so we just return infinity. And the first option that we can choose other than those base case is that we can just choose to not pick this one as peak. We're just gonna ignore numSi. So this is the ignore case. When we ignore numSi, we just move I from I to I plus 1, and we inherit the remain and also inherit its first peak. Another option is we choose this one as a peak. So how do we choose this one as a peak? Is that we need to calculate the cost to make this as a peak, right? How do we know the cost to make this as a peak? We need to know the left and the right value. So we're just gonna pick the maximum of the left and right, and then minus the current one plus 1, because we have to be at least 1 greater than the maximum of these two in order to be strictly greater than both. And of course, if nums I already happens to be larger, this will be negative. So we're just going to put a maximum here, so we won't have a negative value. So in the best case, we just don't spend any cost on this. And then if we choose to pick this one as a peak, we have to move at least I plus 2. Why? Because again, like I and I plus 1 cannot be both peak at the same time. This will violate the definition. And then we just return answer in this recursive call. And then the final answer or the initial state is just going to be DFS 0, means that we start I from 0, and then we still have k peaks to pick from. And then we also haven't decided if the first one is peak or not. And then we're just going to return the final answer here. Yeah, that's pretty much all for the brute force solution. I can explain a little bit what is peak here if it is not so clear. So if I equals 0 and this is the first element, and if it is the first element and we also happen to need to choose this one as the peak, then we will return 1 here. So basically means that the first one has been chosen as peak. So this will be true. true, and otherwise we will just inherit the previous is first peak value. Yeah, so that's pretty much all for the brute force solution. And this will run, but obviously this runs exponentially and it will time out. Let's think about how can we improve the time and space complexity for this problem. So first of all, we are going to comment this whole thing out because this one is too slow. And then we are going to rewrite the same function. Okay, and then we can copy the previous code a little bit here, so this can be reused. And then because we are doing DP now, we no longer need a recursive call. It's just going to be a loop body instead. So the first is I, right? And the second is remain, and the third is first peak. So the first one is I, and the second loop is remain, and the third loop is first peak. And then we are just going to copy the previous loop body into, we're just going to copy the previous recursive body into the loop body here. Okay, let me uncomment them and fix some formatting. Okay, so previously we just returned 0 here. We're just going to change all return into dp I remain is first peak and then continue because we can no longer return. This is a loop body. This is not function. Remain is first peak. And then continue just to simulate the continue behavior, just to simulate the previous return behavior. So this one is similar. dpi remain is first peak goes to infinity, and then again we just return, and this again we just change it to dp. And this is fine, this is fine, this is fine. Keep it. This DFS, we need to change it to dp as well. And then this return, we need to change it to dp I remain is first peak. Okay, so then we need to think about the dimension of this thing. So the dimension, as you can see here, it can go up to, the first one is I, so it's going to be nums kind of be n. But in the worst case scenario, as you can see here, we're going to do I plus 2. So that means if the last element is n minus 1, so n minus 1 plus 2. So generally speaking, we can be pretty safe if we do n plus 2 for the first dimension. We're just going to create a 3D array first. This is how we create a 3D array in C++. dp. So the first dimension, I'm just going to use n plus 2 just for safe, plus 2. And the second parameter is a 2D array. So the second is the remain. So the remain can go up to k, k plus 1 because we are in a 0 index. And the third parameter is just a Boolean flag. So it's just going to be 0 and 1. No, that's pretty much it for the dimension. And then we need to think about how to design the loop order so that we don't access this value without them being prepared. So we need to look at this dp, all this dp. So there are only two places we reference other dp inside the loop body. The first occurrence is here, dp I plus 1. The second occurrence is here, dp I plus 2. So what does that mean? It means that if we are looping I from the n all the way back to the first one, then we will be safe. Okay, so that's the only criteria. So we're gonna loop from the very last one and then going back to 0 and then I'm minus minus and remain. It actually doesn't matter now. Remain k remain plus plus. Oops. I don't know why that happened. 0 is first peak, less than 2 is first peak plus plus. So there we go. And then previously we just return here. I'm gonna copy this as well. And now we just change it to dp as well. Yeah, but this one is still not fast enough to pass the solution. So let's us think about how to further increase the performance a little bit. But the main idea is just here. So in order to make this problem passing the submission test, we have to do some optimization. First, we need to know when to not do this DP altogether. There are like two scenarios. The first one is that, well, if the original given array already have over k number of peaks, then we don't do it. Or the k that we are asking for is more than half of the peak that we can choose. So again, we already said that adjacent element cannot be both peak. That's why the best we can do is having a peak every other element, but if k is greater than n divided by 2, then it would mean that we cannot have enough place for the peak element. So let us just do that. So if k greater than n divided by 2, and it'll just return -1, so it's not possible. And also we have to calculate the existing peak here, and then we're going to loop from 0 or 10. So this L and R we can just copy here. This is trying to make the current number as the peak, and then what will be the cost. So if, I don't know what that happened, if cost equals 0 and then peak plus plus. So if the peak equals or greater or equals 2k, and it just returns 0 because we don't have to do anything there. Otherwise we can keep going. And let us run this. Compilation error, have to and size here first. So this is how we do the boundary check. Let us try to submit and see what is the latest result. And we kind of passed the time, but we are hitting the memory limit exceeded. That is because we're using too much memory here. In the following, I'm going to show you like a usual trick to reduce memory in DP like that. Basically, as you can see, we are not always need to maintain n+2 number of DP array for this 2D array, right? Because if you can see here, we only need to do I+2 and I, and then I+1. So we never visit beyond this free kind of DP array. We never do I+3, we never do I+4, and at the end, this 0 is just the last one that we use. So that's why we can just keep a copy of the free of this 2D array, and that will be good enough. And let me show you how we can do that. So as discussed before, we need I+2, I, and I+1, these three. That's why I'm going to create, let's say a 2D array this time. DPI, this means for just DPI, and then this will have the dimension of the original 2D array. And what else do we need? We need I+1. So this is I+1. This is going to have the same dimension. And we also need I+2. So just do here, I+2. And here, instead of doing, and then we don't need this original large DP array. We just need to change it at DPI for DPI. This one, DPI, change it to DPI. So this is I+1. Then we're going to use DPI, I+1. And this one is I+2, and this is DPI. And finally, this is just DPI because we want the 0, right? We are going from the last one all the way back to 0. So the last time we do DPI is going to be the one that is DP0. And then here, because it's like a sliding window, so that's why DPI+2 will become DPI+1, and then DPI+1 will become DPI. So because again, we are going from the last one back to 0. So that's why whenever we finish one I+2 will become I+1, and I+1 will become I. Yeah, that's looks good to me. Let me double check. Okay, let's try to run code. Solution error. Missing some. Okay, forgot to roll this. So here. Okay, it looks good to me. Let's try to submit. And how do we got accepted? And yeah, it's still not very fast. Maybe if you know there's a better way, and you can leave a comment and tell me. I currently still have no idea how to improve this further. But anyway, it passes. So let me write down the time complexity. So the time and space this time is actually the same. It's going to be it's not the same. The space, because we do this improvement here, this DP improvement here, the space is going to be just, this dimension. As you can see, this is just k, right? Because this 2 is like a constant. And then time will be this k, but times this n, right? So basically we have to do n times k. Yeah, that's pretty much all. And I hope it is easy to understand. And let me know if you have any question. Thanks so much for watching, and I'll see you next time. Bye.